Hello friends, today we will learn about normalization. Okay, so we have various normal forms. First normal form, second normal form, third normal form, BCNF, and fourth NF. Okay, so we will decompose the table into various normal forms. But first NF to BCNF, we think about single valued functional dependencies only. Okay. So what is single valued functional dependency? If x1 goes to y, it means there are two columns, one is x1, second one is y1. Then anytime if x1 comes at LHS, then RHS will always be y1. Okay, like there are two columns a1 and a2, and if a1 is having a value x1, then the a2 must have the value as y1. Okay, so and when we talk about fourth NF, then we'll discuss on multi-valued functional dependencies. Okay, so up to BCNF, it eliminates redundancy because of FD. There will be 0% redundancy because of single-valued functional dependency. But because of multi-valued functional dependency, there may be some redundancy in a relation which is in BCNF. Okay, BCNF relation still suffers from redundancy because of multi-valued dependency. Okay, so we have a diagram here. This diagram says that if a relation is in fourth NF, then it should be in BCNF, third NF, 2NF, and first NF. If a relation is in BCNF, then it should be in third NF, 2NF, first NF, but it may or may not be in fourth NF. Okay, the relation which is in third NF, it should be in second NF, first NF, and it may or may not be in BCNF and fourth NF. Okay, so first normal form. We'll discuss here about first normal form. A relation R is in first NF only if no multi-valued attributes exist in relation R. R should consist only single-valued attribute. So we have been given a relation here. There are two columns or two attributes, SID and phone number. So we can see here that there are two tuples and phone number is containing more than one value. This is called multi-valued attributes, which is not allowed in first normal form. Okay. So this is requirement. First we create a ER diagram. ER diagram allows multi-valued attributes. After that we create relations and we do normalizations, and after that we create RDBMS tables. But multi-valued attributes are not allowed in RDBMS tables. Multi-valued attributes are allowed in ER diagram but not allowed in RDBMS tables. So by default RDBMS table will be in first NF because multi-valued attributes are not allowed. That's what I have written here. By default normal form of RDBMS is first NF. Okay, so we have been given a relation here. There are three attributes, EID, ename and phone number, and we are having multi-valued values here. So we will convert this table into first normal form table. So what we have rewritten every value again. Like here we are having E1, A, P1 and P1 comma P2. So we have rewritten it as E1, P1, A, E1, P2, A. Phone number, we have splitted the phone numbers here in two tuples. Okay, now this table is in first NF because we are not having any multi-valued attributes. Okay, so what will be the candidate key for this relation? Candidate key is a set of tuples, a set of attributes which can recognize every record of the relation. So EID and P number is a candidate key because if we there are unique pairs of EID P number and we can recognize ename. There is a single valued functional dependency here also, which is EID goes to ename. It means where EID is same, then name must be same. If EID is same, then ename must be same. It means EID can recognize ename, and this is called a single value functional dependency, and EID P number is the candidate key for our relation. Okay. Why we need normalization? We need normalization so that we can remove the redundancy from our relations. Okay, so redundancy can be caused because of a few reasons. One is prime attribute goes to non-prime attribute. It always causes redundancy. Suppose there is a functional dependency as D goes to F. Okay, and if D is a prime attribute, what is prime attribute? Prime attribute is a subset of a candidate key. Those tuples which are a subset of candidate key will be called as prime attribute. And if there is a functional dependency given as prime attribute to non-prime attribute, then it will always cause a redundancy. The second reason is non-prime attribute to non-prime attribute. Okay, those attributes which are not subset of a candidate key are called a non-prime attribute, and if there is a functional dependency given as non-prime attribute to non-prime attribute, then it will create redundancy. It will cause redundancy in our relation. The third reason is prime attribute to prime attribute. Okay, so as I told you that prime attributes are the attributes which are subset of a candidate key. Okay, so if there is a functional dependency given as prime attribute goes to prime attribute, then it will cause redundancy. This case is never possible. Non-prime attribute to non-prime attribute to proper subset of secure prime attribute, because this case is never possible. I'll tell you why this is not possible. Suppose there is a relation given here, ABCD, and these are the functional dependencies. AB goes to C, C goes to D, and C goes to A. So what is the candidate key for this relation? We can see here that AB is a candidate key because it can recognize all the attributes of the given relation. So AB plus ABCD, and AB is a super key, or we can say it's a candidate key. Okay, so and here this is candidate key, this is a functional dependency given here, and we can see here that this is a non-prime attribute because C is not a subset of AB and D is not a subset of AB. It means this functional dependency falls into this category. Non-prime attribute drives non-prime attribute. Okay, this is the second case here. In this one is A is a subset of candidate key. Candidate key is AB and A is the subset of AB. And this is C is non-prime attribute and A is prime attribute. It means it falls into the 4 category. C goes to A. But as I said that this case is never possible, because if AB is the key and there is a functional dependency given as C drives A, it means A can be replaced by C here and it will become CB plus barabar C drives A, okay, and C drives D. It means AB is a key, candidate keys are AB and CB. It means this case is never possible. When a non-prime attribute drives a prime attribute, then it will form another candidate key. So we have to concentrate only on these 3 topics. We need to remove this redundancy from our relations. Okay. we have been given a relation here. A goes to A, B, C, D, and two functional dependencies are given here. A derives B and B derives C. So, but D is not mentioned here in our functional dependency. It means that D is a multi-valued attribute. Okay, so and if I want to compute the candidate key for this relation, then I have to always keep D with other attribute, because D is nowhere in the functional dependency. It means nobody can derive D. So if I find the additive closure of A, then I can A can derive only A goes to B, B goes to C. It means A can derive only A, B, C, but it does not include D. So we have to keep D always with other attribute to form a candidate key. Now AD is the candidate key for this given relation. Okay. Yeah. Redundancy level. First NF has more redundancy than the second NF. Second NF has more redundancy than third NF, but less redundancy than first NF. Third NF has more redundancy than BCNF, but less than 2NF. BCNF has 0% redundancy because of single valued functional dependency, but there may be redundancy is possible because of multi-valued dependency. Okay. Now we'll talk about the second normal dependency, second normal form. Okay. For being a relation into second normal form, relational schema R should be in first NF first of all, and R should not consist any partial dependency. Okay. So what is partial dependency? If a prime attribute derives a non-prime attribute, then this is called partial dependency. Prime attribute is a subset of a candidate key, and non-prime attributes which are not the subset of candidate key. Okay. So what is partial dependency here? We can see here that X is a CK candidate key and Y is a subset of X, and if Y recognize A is a non-prime attribute. I'm repeating it once again. X is a candidate key, Y is a subset of candidate key, and A is a non-prime attribute. Then if there is a functional dependency given as Y goes to A, it means it's a partial dependency. I'll give you an example here. Suppose there is a relation given as here, and functional dependencies are given as okay. So what is the candidate key of this relation? Okay, so AB is the candidate key of this relation, and we have been given a functional dependency. Okay, so B, this is the candidate key, and B is a subset of candidate key. It means it's a prime attribute. C is not subset of candidate key. It means C is a non-prime attribute. Okay, so this is called partial dependency, which is not allowed in second normal form. Okay, so there were three cases. If you see here, there were three cases: prime attribute to non-prime attribute. It means this is not allowed in second normal form. Means it causes redundancy, but we have removed this possibility in our second normal form. Okay, so now we have to concentrate only on these two redundancies, and we will remove in further normalizations. Okay, So now we'll talk about third normal form. A relation schema is in third normal form if every non-trivial functional dependency x goes to y with x should be a super key or y should be a prime attribute. Okay, it means that there is a relation given as first of all it should be in second normal form. It means there should not be any partial dependency. What is the key of this relation? A is the key of this relation because A can recognize all the attributes. Now, so this is okay. This functional dependency is okay for third NF because third NF says that if x goes to y, then either x should be a super key or y should be a prime attribute. So A drives B's. This is okay for us because A is a super key. Now we'll look at second functional dependency, which is B goes to C. Now we can see that B is not a prime attribute because it's not a part of candidate key. C is not a prime attribute because it's not a part of candidate key. The same case, this is not a prime attribute. This is not a prime attribute because it's not a subset of candidate key, and D is also not a prime attribute. Okay, fine. But this relation is in second normal form because we do not have any partial dependency here. So in third NF, these two functional dependencies are not allowed. Okay, so case 1, prime attribute goes to non-prime attribute is not allowed because of second normal form. Case 2, not prime to not prime is not allowed in third NF. It means that we have removed these two possible redundancies. Okay. Now we have been left with case 3 where prime attribute goes to prime attribute and redundancy possible. This case is still possible till third NF. And next normal form is BCNF. Relation schema R is in BCNF only if every non-trivial functional dependency with X should be a key, super key. Okay. It means that there is a relation as A, B, C, D. Functional dependency are given as. So this relation is in BCNF because there is only one given functional dependencies and AB, ABCD. It means if there is a non-trivial functional dependency, then X should be a super key. Here there is a given non-trivial functional dependency and X is a super key. It means this relation is in BCNF. It means we have removed all the redundancies. Okay, I'll take an example here. There is a given relation as ABCDE and there are functional dependencies given as AB goes to C, C goes to D, D goes to E. Okay, so this is the example here. So what is the candidate key? This is the candidate key. So AB goes to C is okay. It could be a relation which is in BCNF form. Now another functional dependency is okay. So we can see here that this is a non-prime attribute and this is a non-prime attribute. Okay, it means that the relation is not in third NF. Okay, and we have another relation, functional dependency here, which is this functional dependency. We can see here that B is a prime attribute because B is a part of candidate key. It means this is a partial dependency. Partial dependency. It means this relation is not in, or we can say that this relation is in first NF only. Okay, because this violates the condition of being a relation into second NF, and when a relation is not in second NF, then it cannot be in third NF, BCNF or fourth NF. Okay, so now we have to decompose this relation so that it can become into second normal form. Okay, so our original relation was so we will decompose it as now we'll see after decomposition what are the normal forms for our relations. So here we can find the functional dependency here, which is this one. AB is a super key. It means this relation is in BCNF. Okay. Okay. This is the functional dependency for this particular relation. It means this is also a BCNF because C is a super key, and we are having only one functional dependency here. This relation is also in BCNF form. Okay, so after doing decomposition of this relation into three sub-relations, we find that these all three relations are in BCNF. It means the redundancy has been removed from these three relations. Now we will see if this is dependency preserving or lossless join. Okay, I will tell you in another video what is dependency preserving and what is lossless join decomposition. But here we can find all the dependencies, like the original functional dependencies are applying in decomposed relations also. It means it's dependency preserving. We can find this FD here, this one here, and this one here. It means this decomposition is dependency preserving. And what is lossless join? In lossless join says that if we decompose a relation into sub-relations, it means ending at the, if we do a pairwise comparison, it means a common attribute should be the super key of one relation. See, if we combine R1 and R2, then C is common between both the relations, and C is the super key of R2 relation. It means the common column should be a super key of either of the relation. It means this is lossless decomposition. Now we can see, so we can join first R1 and R2, and it will become R1 and R2. Okay, now we will join R3, and this will become A, B, C, D, and R3 is BE. So B is common between both the relations. Now it has become single relation because we have joined R1 and R2. So B is common between R1, R2 and R3, And B is the super key of relation R3. It means that we can join all three relations back to R, and we will find the same thing which was earlier before doing the decomposition. Hence, this decomposition is lossless, dependency preserving, and the normal form is BCNF. Okay. Hope it helps. Thank you so much for watching my video.